of that. Brilliant. Did you hear this? He used this. X squared plus y squared is r squared. So he wrote 9 minus r squared. The r's out in front, so it gets distributed. It's not a bad problem at all, is it? This will give you the volume of that solid. Isn't that cool? That polar coordinates is awesome. It's so easy when you're dealing with these region of integrations that deal with this. Well, you know the nature of this. Many of the shapes we've seen so far have these cross sections that are circle. Think of a sphere. Don't think of the projection of a sphere onto the xy plane. Oh, circle. Circular paraboloid. Circles. So that's why polar coordinates is going to be like huge, huge help in working these problems. All right. 9r minus what? R cubed. Give it 2 pi. You already theta. Question for y'all. Can I break it up? Can I split that up? I can? Can I write this separately? It's got 4 numbers. Check. I like to split it up if I can. Remember, you can do everything as an iterated integral, but I will split this into 2 separate single integrals. Do each one separately and multiply them in the end, if I'm able to. You could do what the rules are. Number 1, these got to be 4 numbers. Does that work out? Check. The other rule is you got to be able to write this separately as thetas and r's. I can.
Yeah.
I'll have the 9r minus r cubed dr, and what will be the other part? Times up d theta. Do you all agree? So I'm going to do that. I'm going to set that up right now. 0 to 2 pi d theta. Heck, what's that interval? I'll drop it a little bit lower so everyone can see this. This is the beauty of this. I mean, you will not need much room to do this. You'll compute that, then you'll multiply to this interval from 0 to 3 of 9r minus r cubed dr. I mean, no u subs needed or anything. I know some problems you'll need a u sub, but here you don't. What's that interval? That becomes a theta. And when you plug in a 0 and a 2 pi, what's 2 pi minus 0?
2 pi.
2 pi. Boom, that's done. Now multiply that to, what's the integral of 9r with respect to r? 9r squared over 2 minus r to the 4th over 4, and go from 0 to 3. So that's 81 over 2 minus 81 over 4. Here's my answer. 81 over 2, 81 over 4. What is that though? I mean, what's 162 over 4 minus 81 over 4? 81 over 4. And then 81 over 4 times a 2.
162 over 4.
81 over 4 times a 2 pi becomes you should get that after all that. You agree? Yeah? Cool. I got you to back me up. Right? This would have become 81 over 4. But then when a 2 and a 4 makes just a 2 there. Cool. There it is. And that's the volume. So Aiden, I loved your question, but when they ask that, they're being very specific. They're giving you some shape that's above the xy plane. So giving you some shape that's above there. Does that make go with that? Nice. I'm thinking, I guess Aiden, we could still do it. I'm trying to think, like, even if you had a, because I love your question. What if it was a paraboloid that was sticking upside down, and then it stopped down here at like z equals negative 3. Now let's just say this was z equal to negative x squared minus y squared, plus 1, 2, 3, plus a 3. And this bottom thing is, you can still work it though. Thinking, I gotta do this, subtract that. I'd have to take this, subtract that in terms of my surface right there. Does that make sense? You'd still be able to get that solid. As long as when we write in here as top minus the bottom, it's always going to work out to give you the actual volume. Cool?
Couldn't you do it with any shape as long as you just divided it along the xy plane?
There you go. That's exactly right. You cut it off, do 2 separate problems, and add those 2 portions together. Brilliant. That would work as well. So very good point. Fred says as long as you support those two separate integrals above the xy plane, below the xy plane, but then you'd have to know exactly where that surface hit the xy plane, right? But here, if you just had something like this, shifted up 3 notches, this was down 3 notches, I probably, when I set this up, I have to do just what? The top one minus the bottom one, which leads into something, everyone. We're going to get to after polar coordinates. You go, why don't you just set up a triple integral? So it sounds scary, but it's not bad at all. You see what I just wrote right here? I'm going to go a little bit above it, and go like this. This is the same as, put a 9 here, put this down here. We'll put dV for volume, and just put a 1 here. And what would be your first step? Because this would be like now dz dy dx. So what's the integral of 1 with respect to z? Z. And then you plug in a 9, you plug in this, and you subtract them, and you get this, don't you? Does that make sense? So we'll do that in a second, but this is a great problem you were talking about. I'll get this out of the way. We're saying, now we see a need that you can actually write things as triple integrals. And we're saying this could be the triple integral of 9 minus the x squared plus y squared. I'll put a dv here. Whoops. Triple integral, this would be the 9, this is the x squared plus y squared, and I'll just put a 1. So triple integrals of 1 find volume of solids. Triple integral 1, because your first step is, think of this as dz dy dx, right? dz dy dx. What's the integral of a 1 with respect to a z? Just the z, but what do you plug in there? You plug in 9, you plug in the x squared plus y squared, and you subtract them, and it turns into a what? A double integral. Does that make sense? Cool. So that's where we're going with, but don't worry. Triple integrals, they don't get to that until section 15.6. I'll make sure to work one of those, though, before you leave to them. So you get a chance to work with that. So does that make sense? This right here is equivalent to this. Cool. All right. So with triple integrals, can you eventually just keep doing polar coordinates? Yeah, but once you get it down to how many? A double integral. Good. I'll make sure we do another one before you leave with the triple integral. All right. I want to try this one. They want you to find. Okay, they said evaluate. Evaluate the iterated integral. All right, I'll just write integral. They just put a d there. Cosine of x squared plus y squared dx. And here's d, where d is bounded by the semicircle x equal to the square root of 9 minus y squared. And the y-axis. Okay. We gotta evaluate that interval. Hey, you can go back to what you asked before. I think we still gotta treat that as net volume because I don't know what that surface is doing. It's equal to that, right? And it might dip below the xy plane and stuff there. We'd have to know what was happening. So who knows if we're going to get a positive or negative answer out of this right now. We'd have to have knowledge of that surface, wouldn't we? The way this is set up. So they're not asking for volume, they're just saying evaluate the interval. What is that? We know when you get y equal to square root of 9 minus x squared, that's the top semicircle, right? So what does x equal to square root of 9 minus x squared look like? It's a semicircle. Andrew, outstanding. He goes, it's on the side. So it's over here. So this is that region of integration. This is D. He says it's over here, and the radius is what? Alright, that's here. Does anybody know what we represent the part over here? X equals negative that. So you'll start seeing these more and more often. If it's y equal to, it's what? the top semicircle. If it's x equal 2, it's on the side. Cool? So where am I shading? They said D is bounded by this semicircle. We know it has a radius of 3. And what was the equation? And the y-axis, which is where? Did I go there? Sometimes people read this and you're taking you're in test mode, and you're just reading a problem. The minute you see this, people just automatically say, "Oh, semicircle up on the top." But because it was x equal to this, we're thinking this one and the y-axis right there. Does that make sense? So let's shade it. Now, what do y'all think? Do you want to stay Cartesian? No way. That's a portion of a what?
Polar.
How about this? Polar. Look, go polar. Let's go polar on this, baby. Unless you like putting square roots and stuff, right? Square to 9, no. Let's go polar on this. Okay, so I'll start out. Before I forget, what letter? R. RD theta, right? The pirate, RDR. RDR. I'm going polar, RDR. If you ever go, why are we doing that? Students will always ask me like a month later, why do we put that R? It always gets back to that. That's why I want to keep that up here. You can have an idea why we have to put that. All right. Cosine stays cosine. Any suggestions for this though? R squared. Right. Hey, if it just said cosine of x, and any little I would have written cosine of r cosine theta. Right? If it just said cosine of it. If it said cosine of y, I would have put cosine of all that. But when you get this x squared plus y squared, we can just put the r squared there. Cool. All right, we got that. Ooh, the radius is going to be easy. Do you all agree it's just 0 to 3?
Mm-hmm.
Look at the shaded region. From here to here, 0 to 3, 0 to 3, 0 to 3, 0 to 3, 0 to 3. That's how the r is measured. From the pole, they call it the pole. The pole is the origin. From the pole out to the edge of the curve. It's always 0 to 3. Can you help me with theta though? You got to think back to trigonometry. That's the, I love that. You just go from negative pi over 2 all the way up to pi over 2. Remember in trigonometry we rotated this way? We always rotated this way. So that's what we're going to have to put. Negative pi over 2 to pi over 2. Is there anything else I could have used? Because you got to think lower limit, upper limit, right? The only other thing we could have used is, I guess we could use coterminal angles. If I use 3 pi over 2 here, what do you got to use there? 5 pi over 2. Does that make sense? You got to think how it rotated. 3 pi over 2 to a 5 pi over 2, because this has to be the upper limit. That value has to be higher than this, true? Yeah? Is that it? Oh, cool. Question for y'all. Can we break it up? You can. It's funny, we can't always break it up, we get that, but many times in polar coordinates you can split this up into two
So, but
separate
didn't you say to do iterated?
What was that?
You said to do an iterate, right? Iterated integral?
Oh yeah, they wrote iterated integral.
Oh, yeah.
They wrote that, doesn't mean we have to do it.
Okay.
I love his question when he said, when I read the problem from the book, it said evaluate the iterated integral. And iteration means we got to do the innermost and the outermost. We don't have to do that in an iterated manner if we're allowed to split it up, right? By the way, you still know how to do an iterated integral, right? You do this one with respect to r, then you break out the other one. But I love when I can just what? Split this up, which can you tell I can? This is just a what? D theta, that's going to be easy. And what's the r part? I can break this up because I got 4 numbers. True? And I can break it up into thetas and r's. As a product, See, what's that?
Just theta.
Just a theta. This doesn't come out to be 0, does it? Be careful. What's pi over 2 subtract negative pi over 2?
Pi.
That's your pi.
Uh-huh.
And here's my reason I like to split them up when I can. Does that involve a u sub? That's my point. If you get involved in a u sub and you got a double integral on it, it can get really confusing, right? That may annoy you. So I want you to be very comfortable going, hey, I'm gonna break this thing up, I will, just do my u sub. U equals the r squared, right? What's du?
2r.
2r dr. So 1/2 du equals
R
r
dr.
dr. We got a few u subs with these integrals in sections 15.4 and 15.5 and 15.6, etc. I wanna go with that? Alright, let's put it in here. Go in here. What gets knocked out? The r and the dr go away. Now you have the cosine of what? Cosine of u. I think last class, a lot of you like to wait till the end. You resubstitute, so I'll do that. What's the integral of cosine u?
Sine.
Sine u. Now resubstitute. What was u again? R squared? And you gotta go from what to what? 0 to 3. So I get pi times, ready?
Shouldn't there be a half?
Yeah.
Half?
Oh, and a half, you're the best. Everyone, let me put that right here. I gotta remember that 1/2 right there. Alright, thank you. And everyone else, thank you. They're like, don't forget you got a half right there. This is half cosine u du. And I'll put my half right here, and I'll put my half right here. So inside this integral, I get 1/2 of what? Sine of
9.
9? No, just leave it like that's 9 radians. That's an irrational number. Minus, at least we know what's sine of 0.
0.
What's the answer? And I'll put the answer right up here. Looks like we got pi over 2 times up
Sine 9.
sine 9. That's it. Pi over 2 times sine 9. Hey, when you get answers like this, pi over 2 times cosine 9 minus 1, you can just leave it like that. You can leave it like that, that's fine. Did I go that? Nice. Hey,